All right, recording, rolling. It is Tuesday, December 5th. We're going to do a bunch of these Chapter 8 textbook puzzles as planned today. And we did get a start the other day. We finished the first four circled ones. So we did these the other day. Okay. Let's go ahead on down the other circled ones. All right, next one lined up is number 75. Propeller spins at so many revolutions per minute. Is that called RPM? Revolutions per minute? Right, if you guys ever hear that? Okay. So even before I get to the question though, you guys can already imagine we're gonna have to convert that number, right? Right. Guys, we're gonna have to convert that number to what unit before you can do any math? Radians per second, right? We don't want revolutions in minutes. We want radians in seconds, right? Right. Okay. So that's gonna be one step. Oh, actually, that is the first question. Look at that. Right. What is the angular velocity in radians per second? So we'll do conversion right there. Okay. And then follow-up question, what is the angular displacement after 2.5 seconds? Right. All right, so one thing at a time here. Got 75, part A. All right, they gave us, so you guys can see this. Right. Angular velocity. Guys, what's the physics character for angular velocity? Is that omega? Right? Angular velocity? Right. Equals, now they said 1880 revolutions per minute. Right, that's what they gave it to us. Right? Say convert that to radians per second, right? Which we would want to do anyway for any kind of math that falls there. Right? So okay. give you guys a head start there. Right? Just I could go whip in the answer, but we'll walk around the room and see if you guys can solve that before I do. Solve that before I do. So guys know I'm always encouraging you to stay a couple steps ahead of me. That way, it's like more active thinking on your part, right? And then look at my notes and check your answer, right? So hopefully you guys said one revolution is equal to how many radians? 2 pi, right? You guys seen that quite a few times so far, right? 2 pi radians in one revolution, right? Kind of like circumference equals 2 pi r is a specific version of that, right? We also need to convert minutes into seconds, or what, radians per second, right? Okay. So 1 minute is 60 seconds. Okay. And that's going to give us some number, radians per second. Look at that, radians per second. Okay. So look, unit conversion right there. Let's see if I get what you got. Did you guys get like 100? Okay, 196.9. Maybe I'll call it like 197 radians per second. You guys get something like that? Yeah. Okay. And then next question was, what's the angular displacement in so many seconds? Okay. This sounds kinematic. Like we know how fast it's rotating. They told us how much time. They want to say how far, something like this, right? Except it might be like a simplified version of one of those. This sounds a lot like distance equals speed times time. So I think we can just use that bit right there, right? Distance equals speed times time, right? Just like that. Right? That's all we're gonna do. In this case, it's angular displacement equals angular velocity times time, right? So that feeds in there. Got 197 radians per second, or maybe if you kept more decimals, that might be a good idea actually. Okay. This is for 2.5 seconds, 2.5 unit seconds. Gonna gives that so many radians, so many radians. Right. So take my answer, which has all those extra decimal places, times 2.5. Right. I'm getting this many radians. Okay. All right, so almost 500 radians. I'm curious to know how many revolutions that is. How do you convert that to some number of revolutions? Here, let's do another one of these tables. Got this many radians. I know there are, oh, you just do the reverse of what I did right here. 2 pi radians and 1 revolution. Okay, so here I got how many radians? 492. Okay. Let me type something that's incorrect in the calculator just because it still see a number of students doing something like this. Is if I do this, divide by 2 pi. So take my 492 radians, divide by 2 pi. Now the way I typed it in my calculator, I'm gonna get the wrong answer. Wrong answer. Guys, what's wrong with the way I just typed that? What's wrong with that? Yeah, right. The way the calculator is interpreting this is it's dividing by 2, and it's turning around, it's multiplying by pi. Right? So I would get something like 773. I just want you to see that some number that's different from what I'm about to get. I can group the 2 pi in parentheses. So if I second insert a parenthesis right there, and all right, now the 2 pi is all in the denominator. So now it's the correct way. And look, I get a different number. So 78. So it'd be like 78 revolutions is what that is. Right? So if you want to know like how many total turns is that, there you go. Right? Turn around about 78 times, 78.3. Right? Of course, all the math you want to do in radians, and then you can convert after the fact. Right, you guys do that? Very good. Okay, number 76, the next one. The propeller in the previous problem. Okay, so this is a continuation. Slows from 475 revolutions per minute. Okay, so I guess it's going some different speed already, right? To some different revolutions per minute. It does that all in 4 seconds. What is the angular acceleration? Right? You guys can already see there's like a mixing and matching of units, right? I have minutes as a time unit here and here. I have seconds as a time unit here. Right? I mean, we're gonna have to convert to radians per second, but if you didn't know that right away, then the fact that the units are all mismatched, you kind of figure that out anyway, right? So let's convert each of these numbers to radians per second. And then I think we're gonna have to bring in like a full version of one of these kinematic expressions because there actually is some kind of angular acceleration going on, right? So we'll do a conversion for, like, we got 2 different angular velocities. So it's probably gonna be one of these. If they gave us some amount of time this happens in, it's probably gonna be this right here. If they give us how far it turns, then it's probably this third one. Okay, so one thing at a time here. Number 76. Okay, I'll go omega initial, omega final. So let's just do some conversion first. Okay. It was 475 radians per second. It slowed down to only 187. Oh, sorry, that's revolutions per minute. Oops. This whole idea. Right. Revolutions per minute. RPM, you could call it. Right. This many revolutions per minute. Right. So let's do some conversion. Right. I think it's the same conversion which we just did. Right. 1 revolution is 2 pi radians. So 1 rev, 2 pi radians. And then 1 minute is 60 seconds. 1 minute, 60 seconds. Okay. Radians per second, radians per second, exactly what we're looking for. So, 5. So this is telling me this many radians per second. This is telling me this many radians per second. Okay, a little rounding, but I think we'll get close enough. Okay. So there's initial and final angular velocity that we can plug into equations, right? The third piece of information they gave us, they said the time interval was 4 seconds. So they gave us 3 significant digits too, right? I might call that delta t, like a time interval, or t, right? Something, right? Either way, think of it. Right? So we have 2 angular velocities and time. And the question is, what's angular acceleration? Okay. Is that's the job for which one of these? First, second, or third? Yeah, definitely the second one. Right? Because we have two angular velocities, bam, bam. It gives the time interval, bam. They're asking for angular acceleration, bam. Oh, okay, so we have everything except for one unknown, right? Okay, yeah, that's definitely one on one, right? If you pick the first one, then there's nothing to do with the final angular velocity. Also, there's two unknowns, so it's okay. And the last one, well, there'd be two unknowns and nothing to do with time interval. Yeah, okay, so definitely want the second one. Let's go. Final angular velocity equals initial angular velocity plus angular acceleration times time. Right. Solve for this. Right. You could do algebra first or arithmetic first. Right. It's up to you. Here, maybe I'll plug in the numbers first. All that. Right. So we're going to this many radians per second from this many radians per second. Okay. Notice the fact that it's like slowing down. I bet we're going to get a negative value for angular acceleration. Figure out what that is. Okay. This all happens in 4 seconds. Okay. So that minus that divided by that is that. So let's do that. 19.6 rad per second minus 49.7 rad per second. Okay. This all happens in 4 seconds. Okay. There is alpha. So feed that in the calculator and see what we get. Okay. Gotta make sure this is in parentheses. That many radian per second minus that many radian per second, all grouped together, and then divide by 4 seconds. Look at, oh, yep, it's definitely negative. About that many radian per second squared, right? Then, depending on how many digits you keep, some of that, I guess 7.5. All right, guys got that? Ooh. All right, looks like a bunch of fun questions that I did not assign to you. So if you really like the stuff, want more practice, it's a bunch of good opportunities there. But I'm gonna skip on to the next one that I did circle. Yeah, if we have a little bit of time at the end of class, I might go back and hit some of these that I didn't circle. Okay, number 90, topsoil. You got 10 bags of topsoil. It's right here. Right. Each weighs 175 newtons. Ooh, okay. So you have to read this real close, right? Each individual bag weighs 175 newtons. Because it has, side thought here. You know, what's the mass of each bag about? Pretty close to. About 17.5 kilogram, right? 17.5 kilogram, right? Okay. So it's like 17 and a half of these, right? To have 17 and a half of these, your largest lab weight. Okay. It's like a bag, right? But there's like 10 bags, right? So guys, what's the total weight of the stack of bags? So each weight times 10. So like 1,750 newtons, right? I think that's what that'd be. So 1750 newtons of weight, right? And I think we could treat this kind of like a point mass here, right? Okay. So it's on this sheet of wood that's like so many meters long. They're saying 2.43 meters long. If you added these numbers, I bet yeah. If you add these two distances right here, that brings you back to this 2.43 meters. Right? Right. They are stacked half a meter from one end, okay, just like this picture shows right here. So that's all consistent with the picture. Two people lift the sheet of wood, one at each end. So one person lifts to the left, one person is the right. Okay. Did they say the wood itself has negligible mass or negligible weight? Oh yeah, okay, there we go. Ignoring the weight of the wood, right? I mean, the weight, the wood probably has a little bit of weight, but it's probably pretty small compared to stack of topsoil, right? Okay. So how much force does each person exert, like lifting? Right? So you got two people lifting, right? So you guys imagine there's a guy over here, this guy over here, they're lifting this whole thing up. Okay. Before I go plug in and check in on this thing and solve this thing, right? Guys, who has to lift with more force? The guy on the left or the guy on the right? Who has to pick up with more force? See, show hands. What do you guys think? What do you guys think the guy on the left does the heavier lifting? Who says the guy on the right does the heavier lifting? Yeah. This guy's gonna, maybe he's gonna carry more of the load, right? This topsoil is more on his side. So when we get an answer at the end, hopefully the answer is consistent with that, right? The guy on the right. So number 90. Okay. I'm gonna redraw what they have, but maybe I'll do a more cartoony version of it. Right. So looking from the side, here's the plank of wood. Okay. Here's like a stack of topsoil, right? Got the whole stack right here. Right. I'm gonna treat this as if it's applying a single force, bam, right there, of 1750 newtons. Right. I'll say like the collective weight of that stack of topsoil. Right. It's 175 newtons each times 10 stacks. Boom. Right. Then I got a guy on the left side and a guy on the right side. Right, lifting up. Right. So this guy's applying probably a small upward force. I'll call it F sub L. This guy's applying a large upward force. I'll call it F sub R. Right. FL for force left, FR for force right. Okay. Let me check. Hey guys, it's a free body diagram from the side. Okay. So I know my conditions for equilibrium are that the sum of the forces have to go to 0 newtons. Right? Now, in this case, there's only vertical forces. So if you like, you could throw a subscript y on that. Right? I could also say that some of the forces in the x direction goes to 0, but I don't even see any of those stuff. Now you can write that. Okay. But the other condition for equilibrium is the sum of torque goes to 0. Right? That's Newton meters. If you like playing with the right-hand rule, something like R cross F, right? You could throw a subscript Z, like about a Z axis going into out of the page, or if you just want to go clockwise, counterclockwise, maybe we'll see it like that. Right? There you go. Those are 2 conditions you need. Right? Now, if you did not have this torque condition, like a few weeks ago, we weren't at torque yet, right? But you guys knew about forces. Okay? That is not enough to solve this problem by itself. Because look at this. All you would know is that these 2 upward forces have to hold up the weight of the topsoil, but you wouldn't be able to say exactly how much each individual force is. All you know is that the collective force has to add up to 1750 newtons, right? That's what that condition says, right? But how much in each individual person? Well, that depends on the locations of these things. Gotta work on some locations here. Right. We're calling this distance right here. I'll call this maybe like R1 equals 1.93 meters. That's straight out of the textbook, right? And then the full length of this thing, we'll treat this as the pivot point, right? So this is like the, calls the pivot right there. Show you guys why I picked that point too, right? And then the radial distance for the entire length, right? Maybe I should call that L, right? Is the full 2.43 meters. Okay, go like that. Is that all right? That's set up. Right. Now, why did I pick this point right here as the pivot point? Right. There's probably 2 opportune locations. You could technically pick any point as the pivot point. Right. This looks a lot like the most recent lab you guys did. You guys remember the scaffolding lab, right? You had a meter stick, you had a couple of spring scales, you had like a lab weight. That looks just like that, doesn't it? Right? And in principle, you can pick any point as the pivot point, and this condition always holds. The sum of the torque goes to 0. I had you guys sum the torque about 2 different locations to ultimately solve for something, but use that principle. Right? But here's the thing about picking this point as the pivot point is that one of the unknown forces causes no torque about that point. Kind of like if you push on the door hinges of a door, it'll never rotate the door. Therefore, this goes away in this equation, and I have only the other unknown forces, so now 1 unknown in the equation, which means I can solve for it. Right? Alternatively, I could pick this guy on the right as the pivot point and could solve it that way too. Right? But continue with my own setup here. So I'm going to play out this condition, bam, right here. This condition right here. Right? So I'll use this to solve it. Right? I'm going to say R cross F, the sum of R cross F. Right? So from this pivot point, I got R cross F of the caused by the topsoil, saying let's go clockwise. Right? So the sum of torque equals R cross F, that's mg of soil, right? Maybe I'll call it clockwise negative. You usually do conventionally I'll call it negative, right? Then I'll say plus for this now clockwise torque caused by this guy on the right holding the whole thing up. That's at the full length, radial size. There's your radial arm, right? Cross with force on the right, right? This all has to zero out, 0 Newton meters. Okay. Also zero out. So we tried that. Okay. Because once you get that set up, you're probably pretty good to go. You can just plug numbers in and solve for what's this force on the right side. Okay. So let's do it. Let's go 1.93 meters. Okay, this is the negative torque, clockwise torque, right? The weight of this thing is 1750 newtons. Right? Then plus the full length, that's 2.43 meters. This guy, force upright, is holding up. Right? This all zeroes out, 0 Newton meters. Okay, just like that. Then very simply add this torque over, divide by this radial arm, boom, you got your answer. So this force right equals, right, add this over 1.93 meters times 1750 newtons. And then divide those coefficient, radial arm 2.43 meters. Right, let's see what that comes out to. So add that over, divide that down. 1.93 times 1750 divided by 2.43. Okay. I'm getting 1389.9, I'll just call it 1390 newtons. So it's a force. There you go. Right. That's how much this guy on the right is pulling up. Okay. Well, that's one of the guys. Let's figure out the guy on the left. You guys good so far? The torque sums to 0. I picked the guy on the left as the pivot point. Sum the torque about that point has to zero out. Therefore, I can solve for one unknown. Got the upward force here is 1390 newtons. Right? Well, what about the guy on the left? Right. So there's different ways to solve this. I could switch the defined pivot point to this guy on the right and do a similar type process and get this force on the left. I could do it that way. Right? Or, hey, can I just play off this condition right here? The sum of the forces on the y goes to 0? Oh. I could just do that too, right? Right? Because now these two upward forces were originally unknown, but now I know one of them, so I can just solve for them. Let's do that. Let's do this condition right here. The sum to 0. So the fact that the sum of forces, y direction, I guess, like sums to 0 newtons. Right? I've got force left upward plus force right upward minus the weight of the topsoil, it's down, right? Has to zero up. And I know two of those three things. So what's the force on the left is the question. I know the guy on the right is holding up with 1390 newtons. We just solved that, 1390 newtons. Okay. And the topsoil, where that whole stack weighs 1750 newtons. Okay. This all has to zero out. Add that over, subtract that. What is 1750 minus 1390? Okay. I'm looking at left force equals 360 newtons. About like that. Okay. Hey, remember before we even started solving this? I said just look at that picture. I asked guys, show of hands, who holds up with more force, the guy on the left or the guy on the right? And you guys all said the guy on the right. So, oh, the guy on the right holds up more force. Topsoil is closer to him. Right? That's exactly what this does too. Look, the guy on the right holding up with the over 1300 newtons. The guy on the left is only over 300 newtons, right? Ooh, it's about a third as much, about. Right. Let me do one last thing with this. I want to do a final check. Let me go back to the sum of the torque goes to 0 and pick just some other point, right? Instead of this torque goes to 0. Maybe the guy on the right, right? From his point of view. Well, from his point of view, I got R cross F, the topsoil is now trying to make it go counterclockwise, and R cross F, the guy on the left, is going clockwise. Let's see if that actually zeroes out, or at least pretty close to zeroes out. It should be pretty close to 0 out, right? I know this is a slightly rounded number, so it might not be exactly, but some decimal, right? So I got 1750 newtons, and this was 0.5 meters is what this was, right? 0.5 meters, this R cross this F, right? So let's go counterclockwise. So it's like 875 minus, right? This full thing is 2.43 meters and the left force was about 360 newtons, right? Right, so this should be pretty close to zero, right? In comparison to 875, right? So if it's like, I don't know, like 1.1 or something, okay, that would be so small, right? It's like, yeah, it's like 0.2, right? And the only reason it's not exactly zero is because this number is a slightly rounded number, so that's it, right? But 0.2 compared to 875, yeah, basically zeroes out. So we did a check. It all checks out. Right. You guys got it? Right, number 103. Ooh, a banner suspended from a horizontal pivoted pole, as shown in this figure. The pole is 2.1 meters long and weighs 175 newtons. The banner weighs 105 newtons, and it's 1.8 meters from this pivot point on the left. What is the tension of the supporting cable? Right, it's kind of hard to see, but maybe I'll draw this here. Right. Here's the cable, bam, right here. And it says the cable's at a 25-degree angle from the beam. Right, okay. Hey, this looks really similar to a starter question I asked you guys a few days back. Right? This looks pretty familiar, right? It's slightly more, I think this one's slightly more complicated, just a little bit more going on. Right? But yeah, it's all this. Right, so I'll call this 103. Right, so I'm gonna redraw this picture, get some torques going, and we're gonna solve this with torque, just like we did that starter question a few days ago. So here's your beam. Okay. We're saying here's the pivot point. Okay. Now let's say that's like free to pivot about this pivot point where it's hooked into the wall. Okay. They define that as the axis of rotation. I think it's the easiest way to solve this anyway. Okay. We've got this cable at a 25-degree angle going this way. It'll do about we'll do F sub T, which is tension force. Right. This is 25 degrees. Right. They said the weight of the beam is 175 newtons. Right. Now the weight of the beam is distributed over the whole thing, but we're going to put the weight of the beam as if it's concentrated at the center mass of the beam, which is perfectly fine to do mathematically for this torque stuff, right? And that's going to be the geometric center also, if it's all distributed evenly. So that's going to be said 175 newtons. Okay, so I'll call this. Maybe I'll just label it 175 newtons. Right? I think my picture's about to get pretty crowded, so just put the number there. Okay. Okay. Then there's a banner at. Okay, give you guys a location too. Right. So the full length of the beam was 2.1 meters. Therefore, the center mass is half of that, which they also labeled in the book. So it's like 1.05 meters over. Right. So this distance here is like 1.05 meters. Okay, so we get that. Right. I see some R cross F going on. Right. The banner is out at 1.8 meters, which is not quite the full length of it. So this distance right here is like 1.80 meters. Right. That's where this banner is hanging. Something like that. Right. And this has a weight of 105 newtons. Right. So it doesn't weigh as much as the beam. So this is like 105 newtons. Okay. Right. I see an R cross F there and R cross F there. Okay. Now both of those, the weight of the beam itself and the banner, both trying to make this thing turn clockwise. You guys see clockwise, clockwise? Right? What's holding it in check is something about this cable, but this cable is not perpendicular to the beam. Like the other ones are perpendicular, so you don't have to consider any trigonometry. Okay? But this tension, okay, I see a 25-degree angle. I'm going to have to split this tension into components. So, well, that cable is partly pulling up, right? And it's partly pushing the beam into the wall. That's what it's doing, right? That's a really shallow angle too, right? Like if you were worried about the cable breaking, maybe this is a good side question. Like if you were worried about the strength of the cable, or it's like, I don't know if this cable's gonna break or if it's strong enough, right? Would you rather have it oriented pretty much vertically or close to horizontal? They have kind of close to horizontal, don't they? I mean, 25 degrees is a pretty small angle, right? Uh, what's gonna decrease the tension? You guys think if it was oriented vertically, it would not be as much tension? Yeah, I think so. And you can see it right here, right? Like if it was oriented exactly vertically, then whatever this tension force is would be the tension in the cable, right? If it's oriented anything other than vertically, right? Anything other than perpendicular to this beam, and it's only going to be more than that because I see the hypotenuse of a right triangle is always the long side of a right triangle, right? For the same reason. This is also 25 degrees up here if you like, right? So the component of the tension that actually contributes to the torque is not the full tension. It's this component right here, which is the tension times what? Sine or cosine at 25 degrees. Opposite. Which one's opposite? Sine 25 degrees, right? Right. Right. Guys, remember that? Sine is, okay, translates from hypotenuse to opposite, which is exactly what's going on, right? You guys see that, right? Or you could play off cosine of 65 degrees. Same thing. Right. At the point of the pivot, there are also some forces. Well, I know this beam's really being pushed to the left, so I bet it's like pushing back with some force. Maybe we'll call it F sub X, right? And I bet it's also helping support everything F sub Y, right? Maybe there's like components, right? But you know what? If we treat that as the hinge point, we can solve this whole thing with torque. And those two like components of forces don't contribute to torque about the defined pivot point. So we can just ignore those and we don't ever have to solve for those. We can still solve for this tension force right here. This is tension force, okay? With just torque. I mean, solve it all with this right here. The sum of the torque about the pivot point goes to 0 Newton meters. So let's solve it. Okay. So I see 3 torques relative to this pivot point. Here's my pivot. The weight of the beam says let's go clockwise. The weight of the banner says also let's go clockwise. And the tension has something to do with keeping everything in check back counterclockwise, right? So let's do some R cross F's, right? Torque, of course, is R cross F. So let's go at 1.05 meters radial distance. I got 175 Newton force. Now that's clockwise, so I'll call that negative. Right? Then I'll say minus at 1.80 meters. I've got 105 newtons. And I'm saying minus because it's also clockwise. Okay? Then I'm going to say plus, and I'll bring in the counterclockwise guy to zero everything out. Okay? At the full 2.10 meters, that's the full length of the beam. That's also where the cable is. I have Ft sine 25 degrees is the perpendicular component of the tension that's actually providing the torque. Right? So remember, it's not the full tension. It's the sine component of the tension. But so that's 25 degrees right there, 25 degrees. Okay. That all zeroes out, 0 Newton meters. Okay. Like I said, 3 different torques. Clockwise, clockwise, counterclockwise. Torque is R cross F, so I have R cross F clockwise, R cross F clockwise, R cross F counterclockwise. So negative, negative, positive, that zeroes out. Okay. So you guys good with all those numbers? Okay. All right. Once you get that set up, you're pretty much good to go because you just fall back to algebra. We've done like, I don't know, probably hundreds of algebra problems at this point in this class. Right? So I'm going to add all this stuff over 1.05 times 175 plus 1.8 times 105. Here, I'll say this is the middle step. Okay. So 2.1 meters Ft sine 25 degrees equals, okay, and this comes out to 372.75 Newton meters. All right. Then I'll divide this down and divide this down. So take that, divide by 2.1, and then sine 25 degrees. I'm getting the tension is, looks like 420.000. Oh, okay. Maybe I'll just call it 420 newtons, what that would be. Yeah, and then looking back at the original premise, yeah, I think I could believe that. Right? Because what is 420 newtons times sine of 25 degrees? That's 177 something newtons, right? So 177 newtons there. Right? I got 175 down and 105 down. Right? But don't forget that I've got this f sub y that we never solved for, which is, I guess, kind of close to 105, right? All right, there we go. All right. I think that looks like a reasonable answer right there. Right? Got that? Right. So number 7. I think this was like a test question at the end of the book that I thought was pretty good. So, looks like using a wrench to turn a lug nut. Use a 25 centimeter wrench to turn the lug nut on the car wheel shown. Yep, just like that. If you pull up on the end of the wrench with a force of, look at that, 2 times 10 to the 2 newtons. Is that called 200 newtons? Is that what that is? 200 newtons, right? But the advantage of writing this way is, there's exactly 2 significant figures. If you just wrote the number 200, it'd be kind of ambiguous. At an angle of 30 degrees. So we're not even getting the full torque that we could from the force. What is the torque on the wrench? Right. They gave you a huge hint here. Why? There you go. So that's it. Number 7. Right. We got torque is R cross F. Right. And that's the same thing. You know what? Right. I see there's a little twist in this one. Right. It has to do with how they define the angle that they gave to you. Right. R cross F. The sort of definition of that is like the magnitude of R times the magnitude of F times the sine of the angle between them. Okay? But if you look real close, this angle they gave you on this picture, this 30-degree angle, is not actually the angle between these 2 vectors. So this is not going to be RF sine theta. Right? Do you see this angle is relative to this dashed line, which is perpendicular to R? So it's really the cosine component of 30 degrees, right? Like if I break this force into components, I say, well, that force is partly pushing the wrench towards the lug nut. I mean, a little bit of it, right? I guess half of it is really, right? Sine of 30 is half. And then cosine of 30 degrees is the component that's actually causing the torque. So playing off that angle, this is actually RF cosine theta is what it's going to be. So we got 25 centimeter radius. We got a 200 Newton force, and we know that there's 2 significant digits there. Okay. And I'm going to go with cosine of 30 degrees. I know my poster I wrote sine, but careful because that's not the angle that aligns with the poster. Okay. So we've got to switch to cosine. 25 times 200 times cosine 30 degrees. Okay. Looking at 4330 Newton centimeters. You could call that 43.3 Newton meters. Right? But if we only have 2 significant digits to work with, they only gave us 2 digits there, 2 digits there, then really the best we could say is it's about 43 Newton meters. Okay. At 0.3, we don't exactly know. It's like, well, maybe it's like 43.1 or 43.5, but we can say it's about 43. All right. Guys good? Right, number 88, gymnastics. So this figure below, oh, let's look at this figure below. Right. Actually, here, just look at this figure. Probably figure out most of the story just by looking at this, right? Yeah, if you guys ever watch Summer Olympics, I think you see a gymnast, right? So I think it's like the high bar. Looks like he's going around, flying around there, right? It looks like he's gonna fly off and go spinning. It's like spinning in a little ball, right? And it's gonna extend and crash land right there, right? You know what's kind of reminded me of is this rotational inertia table, right? Like when he was at the high bar and rotating around, I think it's kind of like this, just vertical instead of horizontal, right? Probably some version of this, right? When he tucks into a ball and goes flying through the air, that makes me think of the figure skater. You find the poster with the figure skater on it. Where is? Ooh, it's gonna take me a minute here. Here's the figure skater, right? This is like going from extended to going to a tuck position. Right? Probably something to do with this principle would be a good opportune question to ask, right? I bet that's going to be the question or part of the question. It's going to involve that right there, right? It's going to like speed up spinning in the tuck position. Okay. And then, okay, yeah, let's see what the question actually was. Right? Or then goes in for the land right there. Right? Right. So she has a gymnast performing a routine. First, she does giant swings on the high bar, holding her body straight and pivoting around her hands. Yep, that sounds just like this one right here. Then she lets go of the high bar and grabs her heels with her hands in a tuck position. Right. Finally, she straightens up and lands on her feet. Right. Probably has a similar type inertia, rotational inertia that she started with, right? Extended position. Right. Three questions. Question A, and the second, and then the final part of the gymnast routine. So this picture versus this picture, these two. Around what axis does she spin? Ooh, yeah. I guess we could do all three, right? We do all three, right? Like the first one, the axis that she's spinning around, like, is the high bar, right? Which is the center here, right? How about as she's flying through the air? What point is she actually spinning about? Her own center of mass, right? Her own center of mass, right? It sounds like the other day we had the foam boards out. One thing I did was I spun the foam board in the air, right? And it would spin around center of mass. And when she goes for the land, okay. Well, I think like 1 millimeter above the ground, she's still spinning about her own center mass. As soon as she hits the ground and there's some static friction going on, well, maybe not spinning anymore, right? Right? Or if there was any rotation, that could be a rotation point. So like that. Right. So I guess you write down something like that. Right? Rank in order from greatest to least for moments of inertia for the three positions. Right? Yeah, I remember this question from before. I think it's a little bit to interpret. Like, how do you interpret this exactly? Right? So maybe depending on how you interpret this, you might write a little bit different rankings. So this will go with the interpretation and like that, right? So moment of inertia. Well, I think the smallest moment of inertia would be the tuck position. That would be the smallest, right? As I said, rank from greatest to least. So moments of inertia, let's go greatest to least. So these type inequalities, right? And the smallest moment of inertia, let's call this like A, B, C, right? I guess the B, the tuck position would be the smallest moment of inertia, right? Right. Now, A and C kind of look the same, but maybe I think what they're trying to get at is that if you're spinning about different locations, you can have different rotational inertia, right? Like if you're spinning about an endpoint, right? That's like this. We're getting like 1/3 ml squared. Right? There's the mass, there's the height of the person. Versus if you're rotating about your own center, which I think picture C, like if you're coming in for the land, like a millimeter above the ground, you could kind of say that too. That's more like this picture here, like 1/12 ml squared. Okay? You guys see that spinning about your own center is like a quarter of what is spinning about the end, because 1/12 is a quarter of 1/3, right? So I think in frame A, she actually has 4 times rotational inertia of what she does going in for the land. So I'm going to say she has the most in picture A, and then the middle amount in picture C, just as she's coming in for the landing. Okay. That was question B. And then question C, rank in order from greatest to least for angular velocities for the 3 positions. Ooh, great. So angular velocity. Well, if L is conserved, angular momentum is conserved, right? Then, okay. Yeah, let's interpret it like she's like 1 millimeter above the ground in picture C, right? If that's true, then the angular momentum would be the same in all those. Okay. And then angular velocity, right? Omega, 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 right? They said greatest to least, right? So we'll do the same type inequalities, right? So where's she spinning the fastest? B, that second picture right there, right there. Okay. Oh, right. Do you guys notice that where she has the smallest rotation inertia, she is spinning the fastest, right? And if we have the conservation principle, do you guys think you just bam, bam, just going down the line like that, right? Like this be the middle one, and then the greatest inertia has to do with the slowest rate that she's spinning, something like that. Okay. Okay. Now that's all with the assumption that in picture C, she hasn't quite hit the ground yet, right? If you seemed otherwise, the answer would change a little bit. Okay, you guys get there? All right. Ooh, feels like about 10 seconds here. So that's a good pause point right there.